Right, so we'll now move on to the tutorials regarding arches. Tutorial number 11 regarding arches. And I've given you 3 questions to do, yeah? This is a pretty straightforward one, similar to the one we did at the beginning. Find the horizontal and vertical thrusts at A and B and C, and calculate the bending moment at D. The only difference is the load is on the left of C in this particular case. So it's pretty, if you know the method, it should be a cakewalk. This one here has a uniformly distributed load, and we want to find the bending moment at X. So, and this third one, which I'll come back to, is a bit more complicated. It is similar to the arch that I had previously with 2 different radiuses, and we have to find the vertical and horizontal reactions at A and B, and then the bending moment at D, and the thrust and shear at D. And this is the one I'll be showing you how to find the tangent to the circle just using geometry. But let's do it one at a time. So there are 3 problems here. And getting into the first one, where we've got this 8-meter radius arch, 3-pinned arch, with a 10 kilonewton load at D. I've done this a bit differently, and I've taken moments. You might be more comfortable with this than I have done in the lecture notes. So to find VA and VB, we take moments around B, first of all, of the whole arch, of everything on the arch. So we have, taking clockwise moments first around B, we have 16 VA. VA times 16 meters, 8 meters plus 8 meters. VA times 16 meters away from VB. Minus, going in an anti-clockwise direction, 10 kilonewtons times 8 meters plus 5 meters, 13 meters away from VB. So you've got that force going that away, 16 meters, this one 13 meters away from there. This force passes right through there, so you can ignore HA. And all those forces around there must equal 0, because the moment at this pin is 0. We solve this for VA. I'm not going to do the simple arithmetic to do that. Please forgive me. But VA equals 8.125 kilonewtons when you've solved this equation. Now we take moments around A to find VB. And we've got 10 times 3, because we've got this 10 kilonewton load times 3 going clockwise around A, minus, in an anti-clockwise direction, VB times 16, all equal to 0, because the moment there is 0 as well. Solve that. VB equals 1.875 kilonewtons. And I take it you can all see that if you added these 2 together, they total 10 kilonewtons. So the 2 vertical reactions in total equal the imposed load on the arch. And that's important. We now have vertical equilibrium. To find HA and HB, those are the 2 horizontal thrusts, we're going to take moments about C to the right hand of moments about C, the right hand of C only. So cover that up there. We have 8 HB going clockwise at a distance of 8 meters from there. 8 HB minus 8 VB, because VB is also 8 meters from C, equals 0. But you do know what VB is because you've computed that. It's 1.875 kilonewtons. So if you substitute it in this equation and you solve for HB, you'll find that HB also happens to be 1.875 kilonewtons. Okay? And as we said earlier, for horizontal equilibrium, for this thing to be in equilibrium horizontally, HB must equal HA. So if HB equals HA, it's also going to equal 1.875 kilonewtons. And the second part of the question, to calculate the bending moment at D, we're going to take moments about D, and I would suggest at this point that you've got your printed out lecture notes with you, or you've got the first page, not your lecture notes, the first page of this problem there. You've got that in front of you. Of course, we're going to take moments about D for the left-hand side only. So MD, okay, MD equals VA times 3 minus HA times 6.24. This is 6.24. VA times 3, HA times 6.24, which we've calculated using Pythagoras. And that gives you a moment at D of 12.67 kilonewton meters. That's your bending moment at D. And that was all we were asked to compute with that one. With question 2, we've got this uniformly distributed load, and using Pythagoras, we can work out that dimension there, which I'll always draw up a nice sketch that you work with on your solutions. Don't draw some higgledy-piggledy thing. Do it, dimension it properly so it's all clear to everybody, to you and to your examiner, or if you're working in an engineering office, to the person who's going to have to check your calculations, because all calculations get checked before anything is ratified. You're not solely responsible for it, so get into the habit of doing neat workmanlike solutions. Okay, so to find VA and VB, first of all we're going to take moments around B. To find VA, we have 16 VA because it's 8 meter radius again, 16 VA minus 5 times 8 meters times a half of 8 meters, just like we did with the beams. 5 times 8 squared over 2. 5 times 8 is the total load, times 8 over 2, which is the distance from there to there, equals 0, because the moment equals 0 at B. And from that we compute that VA equals 10 kilonewtons. Okay, VA equals 10 kilonewtons. We now take moments around A to find VB. We're going to take moments around A to find VB. So we've got 5 times 8 is the total load, times the distance from there to there, which is 8 plus 4, because half of this is 4. This load acts through its centroid. That's 4 meters plus 8 meters. 4 meters plus 8 meters. So it's 5 times 8 is the load times the arm of the load. Minus 16 VB. VB is acting anti-clockwise around that point, and it's 16 meters away. All equals 0. Solving that, we get VB equals 30 kilonewtons. Checking for vertical equilibrium, 10 plus 30 is 40. 5 times 8 is 40. So your total load going down is 40, and your two reactions total 40 as well. So it's in vertical equilibrium. To find HA and HB, we take moments about C, the left-hand side of C only. So we can do this. the left-hand side of C only. 8 VA, clockwise around there, 8 VA, minus 8 HA, anti-clockwise around there, equals 0, because the moment at the crown C equals 0. Solve that. We know what VA is because we've worked it out up there. You substitute it in there, 10 kilonewtons. Solving for HA, HA also equals 10 kilonewtons. So HA equals 10, VA equals 10. And for horizontal equilibrium, HA equals HB must equal 10 kilonewtons. So there we have the 4 forces, the 2 vertical forces and the 2 horizontal forces. And it is in equilibrium. Now, to calculate the bending moment at X, which is over there, we're going to take moments about X to the left-hand side only. We're going to take clockwise VA times 5 minus HA times 7.41. I'm just having a look at this. HA, not HB. HA, sorry. HA, anyway, there it is, fixed. So the moment at X equals VA times 5, the vertical force times the distance to X, minus HA times 7.41, found by Pythagoras. Solve for VA, well, not for we substitute for VA as well, and for HA. Sorry about that, folks, I've made a mistake here. We're taking moments about X, and we've got VA, which is 10 kilonewtons, times 5 meters, going clockwise around X, and we've got minus HA times 7.41, which is this dimension there, going anti-clockwise around X. And when we complete our arithmetic, we find that the moment is minus 24.1 kilonewton meters. Okay, so that's all done. We can now move on to the final problem in the tutorial, which is the arch that I showed you at the beginning of the tutorial. This arch over here, 50 kilonewtons loading, 3 meter radius and 6 meter radius. And here it is, I've drawn it out again. It always pays to do that. I stuck this dimension in too. Again, similar to the one in the lecture notes, for horizontal equilibrium, HA equals HB, and we're going to call it H. You don't have to write HA and HB because they're the same, H. So we're going to take moments about C for the right-hand side. So taking moments about C for the right-hand side, HB times 3, HB times 3 going clockwise around C, must equal VB times 3 or minus VB times 3. It's the same thing. I mean, you could rewrite this here as HB times 3 minus VB times 3 equals 0. But it's just the same as what I've done over there. So it's just purely a bit of arithmetic. Now, H equals VB, because the 3's cancel out. H equals VB. So we now have 3 facts that we do know. We do know that HA and HB are equal, and we also know that VB there is equal to the forces at HA and HB from equation 1. So taking moments about C for the left-hand side of the arch, moments about C for the left-hand side of the arch, we have VA times 6, VA times 6 clockwise around C, minus h times 6, which is the radius, anti-clockwise, minus 50 kilonewtons times 3 meters, all equals 0, because the moment at C is 0. Simplifying that, we get 6 VA minus 6H equals 150, and we divide through by 6, we get VA minus H equals 25. If you divide that whole thing through by 6, just to simplify it, so VA minus H equals 25, and that's equation 2. Now, we're going to take moments about B for the whole arch. We're going to take moments about there for the whole arch. So I'd suggest, because I can't show that simultaneously on the equipment I've got here, that you get your drawing and the question paper out and look at it while I explain this. You've got VA times 9, okay, the left-hand vertical reaction times 9 is the distance from VA, the horizontal distance from A to B, minus H times 3, minus H times 3, anti-clockwise around B, minus 50 times 6, 50 times 6 meters, and anti-clockwise around B, because we're taking moments around B. Again, when you've simplified that, when you've done the arithmetic, 9VA minus 3H equals 300, divide through by 3, and 3VA minus H equals 100, equation 3. We can now manipulate these equations, and if we bring equation 2 from there down to there, we subtract 2 from 3, and you're left with 2VA, because you change the bottom sign and add that minus VA, it makes 2VA. These disappear, and you change the bottom sign, and 100 minus 25 is 75. So when you divide 75 through by 2, you find that VA is 37.5 kilonewtons. And just for intuitively looking at the engineering of it, you know that this force VA there is going to be much bigger than VB, because this load is to the left of the whole structure. So, right, now we're going to take moments about B for the whole arch, and we've got VA times 9, because we're taking moments around there, VA times 9 meters, minus H times 3, H times 3 meters, going anti-clockwise around there, minus 50 times 6, 50 times 6 meters, going anti-clockwise around B. And when we solve that equation, 9VA minus 3H equals 300, we can simplify it by dividing through by 3. 3VA minus H equals 100. We bring down equation 2. VA minus H equals 25 from there, and we subtract 2 from 3, which leaves us with VA equal to 37.5 kilonewtons. And from that, we can make the assumption that if VA is 37.5, then VB has to be the difference between 37.5 and 50 kilonewtons, because we want vertical equilibrium. If VA is 37.5 going up there, then this must be 12.5 going up there, because the sum of those must equal that load there. And so we've answered the first part of the question then. H is 12.5, VB is 12.5, and VA is 37.5. So there we have it. The two H's are equal. and VA 37.5, VB 12.5 kilonewtons. That answers the first part, not that difficult. We then move on to work out the bending moment at D, and I've drawn this out again. This dimension from the baseline of this part of the arch to D is, as we did earlier, the root of 6 squared minus 3 squared, 5.19 meters. That dimension there is 5.19 meters. So we're going to take moments around that point and ignore everything to the right of that point in doing so. So the bending moment at D, moments about D to left-hand side of D, 37.5 times 3 minus 12.5 times 5.19, which gives you a bending moment at this point of 47.625 kilonewton meters. Is a bending moment at D. Right, quite straightforward to there. All we have left now is to find the tangent, the angle of the tangent at the load. And this is the plain pure geometry of it. We've got this, we know when we've done the 6 meters and the 3 meters, we know that this angle, if you've got 6 meters and 3 meters, that this angle is 60 degrees. If you drop a perpendicular down there, and if that's 60 degrees, the 3 interior angles of a triangle equal 180, so that angle there is 90, of course. And in the 2 interior angles of parallel lines are 60 degrees. From that we can compute this. It's 30 degrees. Okay? Because that's 90 degrees. That's 60, that's 30, that's 90 degrees there. So the angle of the arc, the angle of the tangent to the arc at the point, at the load point, is 30 degrees. Quite easily done. And what do we have at that particular point? This is the point D where the load is. We have a horizontal thrust HA of 12.5 kilonewtons, previously worked out, but shown over here again. We have a vertical force of 37.5 kilonewtons. What we wanted to compute is the shear across the arch there, S, which we'll call S, the direct thrust, which is N. Those are the two things we're looking for. So again, we take the force components of the 12.5 kilonewton HA, which is the horizontal thrust. We've got 12.5 kilonewtons moving from left to right. There it is. 12.5 kilonewtons. We know that this angle is 60 degrees. This one is 30 degrees. Using trigonometry, we can work out what S is. Minus 6.25. Why minus 6.25? Because it is coming down this way. This force is going up. Your thrust, 10.82, positive. Shear is coming down, negative. So there are the two force components for HA, for the horizontal reaction at the bottom of the arch. We now look at the force components of the vertical reaction of VA, and we've got a VA of 37.5 kilonewtons. There it is, 37.5. That line there is 37.5 kilonewtons long. And again, using our triangle, it's actually really, if you open it up, it's an equilateral triangle. All three interior angles are 60 degrees each. But anyway, be that as it may, we know that this is 37.5, that is 30 degrees. We've got the shear going up in this particular case, and we've got the thrust also going up. There we have them. S equals 37.5 cos 30, which gives you plus 32.47 kilonewtons. That's the shear. The thrust is 37.5 sine 30 N, 18.75 kilonewtons. And if you drew this thing to scale, you'd be able to scale those as well, just by pure geometry. Our final loadings, we sum the shears. We add these two shears together, minus 6.25 plus 32.47 to get a final shear force of plus 26.22 kilonewtons. We add the two thrusts together, plus 10.82 plus 18.75, and we get a total thrust at D of 29.57 kilonewtons. And that is the whole thing. But I would suggest to you that you actually get on top of this particular problem, just as a word of friendly advice. Thank you very much.